want to introduce Tom Zawodzinski, who is a expert on fuel cells, to tell us about those opportunities this morning. Thank you, Tom.
Thank you, Nancy. Good morning. I was asked to speak about electrochemical or energy storage in general. As an electrochemist of sorts, I thought I'd do two things to the topic: talk about electrochemical energy storage and actually add conversion. And then finally a little tagline, because in fact, as I'm sure you know, you all have batteries, have been using batteries for a long time, maybe not so much fuel cells, but in fact, these are old and well-developed technologies. Why are we interested in them again? Well, that's part of the story. But in fact, there's been kind of a very strong change in the mode of development that was spearheaded, in fact, by the fuel cell side of things. Batteries, if any of you, I know some people here are involved in it. The battery field is a very empirical field. Fuel cells were one of these rare fields that developed, sort of in an organic way from things that we learned often in the laboratory, not just through building things in industry. So there's a very interesting dichotomy there. So again, electrochemical energy storage and conversion equals fuel cells and batteries. I also happen to be thrust leader for 10 score, our Tennessee EP score. And before you hiss about things, I didn't wear anything orange. I have no skin in this game, although they were speculating that the bleeding fountains were bleeding orange yesterday, but not quite. All right. Many of you, I'm sure, are aware of the interesting things that are happening with electric vehicles these days, and that is heavily driven by batteries. There's one big problem. The battery that we're all familiar with that's great for your flashlight isn't necessarily a great thing for your car. And in fact, some of the growing pains, let's say, of the pure electric vehicle industry have been well publicized. Things like fires and the so-called introduction of the term bricking, namely your battery goes completely dead when you thought you had plenty of charge in it, and so on. However, batteries, there's a lot of interest right now because of the intermittency of renewable energy sources such as wind and solar, and some focus on the electric grid and stabilizing it in various ways, of having large-scale batteries for grid energy storage. I'll talk about that most extensively as we go forward. And then finally, fuel cells, a little interesting PowerPoint glitch there. Fuel cells are, as Nancy mentioned, something that I personally have spent about 25 years of my life working on, whether they're for electric vehicles, stationary applications, or portable power. There's different aspects of these things, and I want you to stop thinking about batteries and fuel cells and start thinking about a continuum, because in fact we're going to fill in the middle of the continuum, at least partly, in a minute. But a battery is strictly speaking, the standard thinking about it is that it's an energy storage device that contains all its reactants. So basically, if you have some waste product, you're carrying it around for the life of the battery. That tends to create a large divisor, which is weight. When people talk about the most important figure of merit of specific energy density or specific power density. Specific means divide by weight. Trivially, and so batteries can be heavy. Meanwhile, fuel cells reactants are externally supplied. So a fuel cell plus a tank, if you will, a tank of something, fuel specifically, is a battery equivalent. The advantage that fuel cells tend to have is that they convert these reagents rather than carry around the waste products. And furthermore, they don't even carry around the reagents all the time. They may, most often, fuel cells will use air electrodes. And so you don't, since all you're doing is carrying around a small amount of catalyst, that divisor that I talked about can be very favorable. Here's some more ways of thinking about things. Battery materials evolve during use. After all, you can only stuff lithium ions into and out of and pull them out of a lattice so many times before that lattice starts to pulverize sometimes or evolve, let's say. The fuel cell device, as I mentioned, is a converter, and so our durability issues are different, totally different from those of batteries in many respects. It's basically how well our catalysts stay active, whether they get poisoned, et cetera, et cetera. Charge and discharge in a battery is slow. It's pretty much on the same time scale as or having to recharge your battery for the same amount of time as you discharge it is an issue that may be the killer for battery-powered electric vehicles, strictly battery-powered electrical vehicles. Whereas in a fuel cell, charge and discharge are the equivalent of filling a tank, which we all are very familiar with because we do it with our gasoline-powered cars. Battery, again, is an energy storage device, and a fuel cell is an engine. And so the important thing there is we also know about the hybrid electric vehicle model. And in fact, you're going to use both fuel cells and batteries in any purely electric vehicle that's based on fuel cells. So right away, I'm telling you, it's not either or. It's both and, you know. And in many cases, we live in a world where what Diederik talked about happening at NSF really does happen at DOE. When funding for one goes up, the funding for the other goes down. It's like sitting on a balloon. But these devices look exactly the same inside, except for details of chemistry, which is kind of interesting for us. Okay, so here's the recent development directions, and the idea is to give you a flavor of what's happening right now in the world. Batteries for electric vehicles. A really major issue is the range of the cars, of the cars. It's today focused on lithium-ion technology, although there's plenty of nickel metal hydride batteries out there. There's a strong need for greater energy density, and that translates to range per weight. Obviously, you have to pull the battery along with the car as well, and so weight is a very important factor. Volume also a very big factor, and those things tend to correlate. So you need greater capacity. You need every battery to store more energy. That has implications for what is built, specifically things like thicker electrodes and so on and so forth. You need longer cycling lifetime. And the cycling, again, for these batteries is very different from the typical cycling that you will have in even in a rechargeable battery like that in your computer. You need better chemical stability. Lithium batteries blow up and catch on fire whether we like it or not. No matter how many controllers people put on them, they seem to manage to burn down a factory that contains a measurable % of the world's supply of lithium-ion batteries every year. And we need faster rates. Batteries are not high-rate devices. The currents that are drawn from a typical battery are sort of 2 to 3 orders of magnitude lower than we're used to in fuel cells on a per square centimeter basis. So again, emerging technologies. People really have talked a lot about lithium-air batteries. We can go back, if you will, to lithium-metal batteries, which the lithium-metal side, half of the lithium-air couple. The problem with lithium-air batteries, there's basically 3 major problems with them: the anode, the cathode, and the electrolyte, which is basically the entire battery. Lithium-air batteries are represent a very difficult series of problems. I have colleagues who work on these who like to use titles like take the worst of the fuel cell and the worst electrode in the battery and put them together and you've got a lithium-air battery, let's go for it, or things like that. There's a lot of hype about this, and basically my read on them is that the lithium-air batteries are really kind of at the stage where we were 20 years ago for fuel cells. In the middle of this continuum are batteries for electric grid energy storage. These are my favorite flavor of these are Redox flow batteries. You can build gigantic batteries, sodium sulfur batteries, and even gigantic lithium-ion batteries. A lithium-ion battery that is as big as a trailer is nothing more to me than a bomb waiting to go off or a terrorist target. It's a real big problem from my perspective. And if you talk to the electric utilities, as I have, back when I was in Ohio, we sat down with AEP, and talked about safety. And their attitude is, if it can explode, it will eventually on the grid. And again, putting a megawatt worth of lithium batteries all together is a real recipe for disaster. These redox flow batteries have a slightly different configuration, and it's actually halfway between a fuel cell and a battery. So you store the reagents externally and flow them into a converter. So you independently actually size, if you will, the power, the size of the converter, and the energy, the size of the tank that contains reagents. Okay, there's some really neat attributes, but I like to talk to people and say, imagine a battery the size of a Home Depot. That's what we're talking about here. As a matter of fact, it may be that you have modular sub-modules of these things, and maybe I saw one recently that's very well packaged of a particular technology that's about 15 kilowatts in a crate, in a sort of a big box that would be put all together, each having their own little tank. But again, this is the core of the technology. Once again, by the way, I didn't put it here, but this is courtesy of my buddies at Electrosynthesis. Convenient web meme now for flow batteries. But in fact, you have, again, electrolytes in 2 tanks or more, perhaps, or fewer, perhaps, depending on the chemistry you use. And you flow them in, and they get interconverted. I'll show you a little bit of a video, if you will, of that in a minute. And of course, power electronics are very important. You have a few pumps that you don't have in a normal battery. So when you start thinking about the system, of course, you have to start thinking about the ancillary components as well in terms of their efficiency. However, as systems go, they have potential for very low cost. They have inherent scalability. I kind of just illustrated that quickly. They're very efficient. You can get up to on the order of 90% round trip, 80 to 90% round trip efficiency, although that's not necessarily the point where people will operate them, I'm learning. This is based, again, on that converter technology that I talked about for fuel cells, except it's actually quite a bit simpler in that you don't, for example, use nanoparticles of precious metal to do your catalysis necessarily. And so that tends to be one of the biggest things that degrade in fuel cells. And so, but we still know that fuel cells are projected to 15,000 type hour lifetimes, which is a pretty good period of time. It's almost 20 years, in fact. And then finally, I emphasize safety. These are often, as I'll tell you in a second, aqueous solutions here. That's actually a plus and a minus, but from a safety perspective, it's a clear plus in terms of the lack of very super high energy density storage of all the reagents together by separating them in these tanks. Okay, there's many types of flow batteries. There's the all-vanadium battery, which we've used as sort of a starting point in our work. Iron chrome, iron cerium, zinc bromine, hydrogen bromine, et cetera, et cetera. There's several new players, especially those using air electrodes. I mentioned lithium air, but there's aluminum air, zinc air type batteries that, if they're made rechargeable, can work. Note that they have several characteristics. Simple inorganic redox couples tend to be cheap, tend to be electrochemically reversible, therefore not killing you on efficiency, and simple, usually aqueous electrolytes. I want to go back for a second. Oops. And show you and remind you about the size of this tank. You know, I have colleagues, and in fact, I sometimes think myself, having done my PhD in this area, about ionic liquid-based batteries or non-aqueous-based batteries. Well, there's not enough ionic liquid in the world to fill that tank, and bluntly, even if there was, it would cost you. You can't get cheaper than water and sulfuric acid, which is usually the electrolyte. But ionic liquid is a good way to make it a lot more expensive. Same with almost any non-aqueous solvent. And you mitigate, for example, if you use acetonitrile or any of the common amides that have high dissolving power or whatever, you will create extra safety problems, once again, because they often are volatile and degrade and so on and so forth. So generally, You need a good voltage separation of two redox couples. That's about it. That energy density depends of course, directly on the voltage difference, and also on how much of it you can pack into a solution. That's another mistake that a lot of the non-aqueous and/or molten salt people make. People rarely use the actual molten salt species as the carrier, but rather use it as a straight solvent, which is a very heavy and expensive solvent to put a tiny bit of lithium into an ionic liquid, and it just doesn't make sense. You can use complexation and other tricks. I went to a colleague who's a real expert on complexation at Oak Ridge. Builds all sorts of interesting ligands to do complexation. I said, oh, we can control the voltage very nicely, et cetera, et cetera. He said, well, why would you want to do that? You're just going to make it more expensive and less soluble. Interesting perspective. I was offering a guy, joining in and getting some funding or something like that, and oh well. And cost is clearly an issue. Basically, our competition is not other flow batteries or other battery technologies, but it's gas turbines. It's pumped hydro. Well, of course, that's somewhat limited. Compressed air energy storage. So we are, right from the beginning, very strongly sensitive to that. So here's a little bit about a redox flow battery, a vanadium one we're going to talk about. I call this, in the immortal phrase of Alfred Hitchcock, the MacGuffin for our work, because in fact it's what's starting the action. And basically we have two electrodes surrounding a separator or an electrolyte, typically an ion exchange membrane. And basically we feed vanadium-2 and vanadium-5 during discharge of the battery, and lo and behold, we create vanadium-4 and vanadium-3, and colors change. Vanadium's really colorful chemistry, 4 different oxidation states. Here's what we're doing at Oak Ridge on this. We're really trying to focus on increasing the power density using lessons we learned from the fuel cells. We're lowering, in light of that, we're looking to lower the aero-specific resistance, and we're starting to implement a durability program to understand these things. But our real goal is improving performance and providing diagnostics. 2 minutes, wow, I gotta hurry. So we've gone we've managed in several steps to improve the power density of these things over the last year and a half by about a factor of 10. Increasing this power density mostly requires engineering, including internal resistance, mass transfer, things like that. The real opportunity is improving the chemistry, as I talked with Steve for about 2 seconds about earlier. Using air electrodes, as I mentioned, air is free in a sense, metal electrodes, multivalent species. There's a lot of ways to work on this and a lot of opportunities. In fuel cells, to quickly shift gears, the cost has been a real driver. You're going to see fuel cells on the road in 2015, much like you saw the first hybrid vehicles some time ago. And the costs are coming down. Right now, I think DOE says it's about $49 per kilowatt installed at high volume. That's pretty good, and in fact, is enough definitely to launch vehicles. Research we're doing, I'm going to have to go fast over this. I'm showing this for the wonks in the audience who like catalysis. We're making various platinum nanotubes and organometallic complexes. Back to our battery and fuel cell comparison, the real important things are here. Basically, almost all car companies, though they've embraced batteries because they were bribed to do so effectively for battery electric vehicles, fuel cell vehicles today have range at least 300 miles in essentially a production, a van that you would not recognize as any different from a Chevy van or a Toyota van right now. Again, higher low T degrades this, but not quite as badly as for these. The recharge time is a real killer, up to 8 hours basically if you drive for 8 hours. Here it's, of course, 3 to 5 minutes because if you use hydrogen as a fuel. Costs are going to be similar with subsidies and so on. Lots of opportunities for chemists, and that's what I am, so I thought I'd throw that in here. A few general ideas. Improving the electrolytes for voltage stability, new nanostructures. This flow battery has a lot to go. I want to close, other than acknowledgments, with A comment on hype and new technologies. This is a slide from the Gartner group that I love and I usually use in public audiences. Basically, it shows something like what Diederik was talking about with the Valley of Death and so on, but it's for emerging technology. If something happens in the lab and you start to get a trigger, people get all excited about it, and you reach a peak of inflated expectations. This is usually when the IPOs are trying to happen. And then basically hard reality hits in, things drop, and you get the trough of disillusionment afterwards. Slowly, those of us who are knowledgeable in the field will keep at it, and you'll have a slow, steady slope of enlightenment before you actually introduce things. So we've gone through this in fuel cells. And hopefully we're on the path to productivity. But I just want to give my contact information and talk about Tennessee EPSCoR. I tried to make orange and blue. Lots of ways we can collaborate, and I will stop with that. Thank you very much.